Okay, welcome. So the topic of this afternoon is mathematical modeling of cancer evolution. So as Susanna said, the word evolution here is not exactly the same as what we talked about earlier in mathematics, because we are mathematicians. An evolution equation is something that just describes how something evolves over time in general. So it doesn't have to be like grand, long mutation timescales. It can be shorter timescales. So basically tumor progression, when we model that, we call that an evolution equation. There will, however, be a little tiny bit about evolutionary pressure at the very last slides. But we have a long way to go before then. Okay, so first off, a bit about me. I am a recent PhD graduate in applied mathematics from Chalmers University of Technology in Sweden, and here we have our sort of beautiful campus in the background. And what I've worked with during my PhD is mathematical models of cancer cell migration, and more specifically, I've been doing statistical inference on such models, where I've looked at in vitro data from mainly glioblastoma cells, and then I've tried to basically perform inference on some key parameters that I have defined in my models for the cell migration. So yeah, my interest in general lies in spatial models of cancer cell populations, and that's we're in luck because that's the topic of this afternoon. So yeah, what is a mathematical model? So a model in general, it's an abstraction of a real-world object or phenomenon, and it's used to study and understand the subject of that model. Why? Okay, that was not supposed to disappear with this click, but let's deal with it. So the subjects at hand, they are referred to as variables, and their relationships is like what piques our curiosity when we study some phenomenon in nature or society. And of chief importance are the equations that govern the core mechanisms of this thing that we are interested in. So, why did it disappear? Oh, and now it's here? Okay. Yes. So anyway, the behavior of the model in turn depends on some parameters that you can feed into the mechanisms, and that will like tune how the model will behave. And then the model will output a couple of dependent variables. So it's like, this is the broadest way that I think we can define a model. So I will like give a brief example from physics. I know that everyone here has like a very different background, but I think that we all know that you can kick balls, right? So let's say that we are kicking a ball, and the kick gives it an initial speed that we call S0, and it's kicked at an angle theta. And we ask ourselves the deep scientific question, what combination of S and theta will make the ball land here? So in physics, they have had mathematical models, integrated with the whole science for the last 500 years. Those include Newton's equations. So we can like apply Newton's laws to this ball. We make a force diagram, do some F equal ma stuff, and then we can calculate exactly where the ball will land, given an S and a theta. Is everything readable, by the way, even if you're in the back? Yes. Good. It was not readable yesterday. Yeah, so in this example, G, which is the gravitational pull of the Earth, is a parameter, and theta and S are our independent variables, because we can change them however we want. And the mechanisms of this model, they're given by Newton's laws. And X, where the ball lands, that's the dependent variable. It depends on the model, the parameters, and the independent variables. But not everything that involves mathematics representing reality is necessarily a mathematical model. This is something that I've realized when I speak to applied scientists. Because, for example, we can kick the ball a whole bunch of times and make a table for, okay, so we had this speed and that angle and it landed here, blah, blah, blah. And then we make some kind of interpolation, like a spline interpolation or some type of regression. And it will sort of give a model for how the ball kicking works, but I would call that a statistical model because it's based on the data that we have. instead of a mathematical model that is based in mechanics that we assume that the ball has. So I have done mechanistic modeling of tumor growth. So it's not that data-driven, it's more driven by like looking at how nature works and then jotting down some equations. And when it comes to jotting down equations for how things work, we are playing catch-up to physics, because physics has been doing this for 500 years, biology for like 50, maybe 60 years. But mathematical modeling is fairly widespread in biology, at least in certain circles these days. And one of the reasons that we are so far behind is because biology is incredibly difficult and complicated. So like in physics, every electron is the same as every other electron, and that will never change, and that's awesome. Then you can formulate good equations for them. In biology, no cell in the universe is the other cell alike. So you can't have these clean, pure relationships that physicists have. So yeah, modeling is much harder, but we can make some good models in biology. A good model, I identify it here as having scientifically sound mechanisms, meaningful, measurable parameters, and like distinct roles that are played by our variables. So one of my favorite examples is a model that was developed by the great Alan Turing in 1952. You're not supposed to be able to read this, but he formulated a set of cool equations that when you solve them, basically the result, given like some initial concentration of morphogenic chemicals, it gives you the pattern of animal furs. So it's like the creation of animal fur patterns could be fairly well described, like really well described with this model. But of course, animal fur doesn't care about differential equations, so all models are wrong, but some are useful. And in this case, with the animal fur, super useful, if you're interested in patterns. So yeah, mathematical modeling in cancer biology in general. So as far as I know, this has been a thing since like the 1960s, where some extremely simple models were applied to tumor growth. And they have proved useful in, like, for example, in silico drug testing, where the effect of a compound on a tumor can be simulated before clinical trials. So you have like a digital medication, a digital tumor, and then you can simulate how these guys will interact with one another. And I found a survey paper, or what is it called? A review paper, yeah. That was called A Review of Mathematical Models for Tumor Dynamics and Treatment-Resistant Evolution of Solid Tumors. And if you like papers that have long tables of equations that people have used over the years, this is a paper for you. But the benefit is not only one way, because cancer modeling, it's extremely challenging, and that facilitates the discovery and refinement of new mathematical methods. So thank you for giving me a job. Okay. So today we will explore and derive some commonly used, what we call toy models applied to cell migration. And yeah, the application in mind is tumor dynamics. We will bridge the gap from microscopic models, where like we take every individual cell and how they like interact with one another into account, and we will blow that up to macroscopic model, where we just look at like the tumor as a whole thing. You will hopefully get some intuition for how to read and interpret mathematical models, both the microscopic and macroscopic scale. And a key concept, I added this right after lunch, is that equations are just sentences. And learning to read these type of sentences can be very, very, very useful. You don't have to know how to solve every equation. That's like the mathematician's job, but learning how to read. So you can basically go from being like this at the beginning of this session, and in like an hour, you will look at this guy, and you will be like, yeah, I know exactly what's going on here. Okay, so let's start simple. We start with like non-spatial models. And I am going to have to introduce you to something called Markov processes. How many people here are familiar with like Markov process, Markov chain? I would say about 2/3 to a half, somewhere around there. Okay, good. So basically, this is the fundamental mathematical object that underpins everything here. So a Markov chain consists of a number of states, and you can like be in one state, and after a random time, you jump to another state. So it looks like this. We have like our simple example here, we have 3 states, and these Greek letters here, I know Greek letters are scary, but you will see a lot of them, represents the rate at which you jump from one state to the other. So if we are in state 1, the moment we arrive in state 1, so we are this orange ball here, we will generate 2 random numbers. So they're tau 2 and tau 3. So tau 2 is the time that we will sit around in state 1 until we jump to state 2, and tau 3 is the same but for jumping to state 3, and they depend on these rate parameters here. So when we generate these random numbers, if tau 2 is then less than tau 3, then that's the state that we're going to jump to next. So after hanging around in state 1 for what we call a holding time, very important to remember holding time, the amount of time we spend holding onto a state, we hang out there for tau 2, and then we jump to state 2, and then we start this all over again and generate 2 new random numbers, so we can jump either back to state 1 or state 3 after a random time. And this is the basis for the most basic population dynamics model that there is. And it's called the birth-death process. So let's give a little survey of it. So the states in the birth-death process correspond to population size. And let's say now it's a population of cancer cells. I wanted this one to appear. Okay. So we have a couple of states. So this state here says that there are n cells in our population right now. We hang around in this state until one of our 2 holding times are reached. So one of them is a model of cell birth, and the rate for cell birth is given by R, and one is a model of cell death, and that's given by delta. So we generate 2 random numbers, check which one is the smaller, and if the death number is the smaller one, then we will jump up the chain to a population size of n minus 1. And if the birth number is the smaller one, we will jump down the chain from a population size of n to a population size of n plus 1. And we have to be interested in something here. I told you about variables earlier. We have to know what we are interested in. And what we are interested in is the probability that there are n cells at time t. That's very, very long to write. So we're going to write that as PNT instead. It's basically how notation works. You write something short. So we're interested in the probability that there are n cells at time t. And then we will try to derive an equation that explains the dynamics for this. Okay? And the strategy for deriving such equations, like if we have have what is called like a stochastic process, something randomly going on, is that we look at where we are right now, and then we look a little bit time into the future, and then we try to approximate like the probability of where are we like one more of us, like one less of us, is it the same? So we like try to approximate these probabilities, and that's much easier for a short time scale. Okay, so we will now formulate an equation for the probability at time n, at time t plus delta t, and delta t is a little time step, that there will be n cells. So how can we arrive there? Well, one way is that there were n minus 1 cells before, and a cell division occurred, which means that we have now jumped up the chain and we have ended up here. So that, a division occurred in the time span between t and t plus delta t. And another way we could arrive there is that we already had n cells and nothing happened. That's also a way that we could have arrived at being at n cells in this short time span. And the third way, of course, is that we had n plus 1 cells, but one of them died, so we have now dropped down from this state to that state.
Sorry, what does it mean like the t and comma t plus?
Oh, it's a time interval.
According to it, probability like t, comma t.
here's the timeline. And we are here at time t. And then we have like a little step into the future that is of the size delta t. So this time is then called t plus delta t. And when I write this bracket, t plus delta t, I mean any time within this interval. So it's a time interval. Everyone follows? Good.
Can you hold that slide for like 1 more minute?
Yeah, sure. Take your time. Did you want a full minute, or can we can we move on?
It's good that you're a mathematician.
Yeah.
Full minute, okay.
Okay. It's fine. So basically, I mean, we can jump up and down, and these are probabilistic things. I used to have like 20 slides showing the details for how to calculate these probabilities, and then I was wisely told that that would be a waste of time. But something that probably isn't a waste of time is a lightning calculus like refresher. So in Swedish high school, if you want to do any natural science in university, you have to take calculus in high school. So I just assume that everyone knows what a derivative is here. Then I heard that wasn't true, so I'm just going to talk about derivatives for a minute. So the derivative of a function is the slope of its curve at some point in time. And we arrive at it by considering what we call here a limit. So what we have here is f of t plus delta t, so that's the time step into the future. F of t, that's now, and then we divide it by how big that step was. So we get it something like this. So here, delta t is pretty big, so we have basically calculated the slope between here and here. Then we shrink delta t, and the slope will, as we keep shrinking, exactly match the slope of the curve here. And this is incredibly important because in everyday language, how you interpret derivatives is rate of change. Like how much is this thing that we are modeling changing right now? And when you model things, you want to know how they change. So that means that we are going to see a lot of derivatives today. But yeah, so as I said earlier, equations are sentences, and this thing is a sentence that says rate of change at the time t. Okay, so after skipping a lot of slides of detailed mathematics, we can arrive at a, let's call it intuitive equation that looks like this. So what we want to model, what we are interested in, is the change in population size. And that's equal to the flow up from a smaller population. So that was like we had n minus 1 cells, then one was born, and now we're at n cells. And it's also plus a flow down from a larger population. So we used to be one more, then one of those guys died, and now we're down at n cells again. And then that's minus us leaving this state. So written as an equation, it's going to look something like this. Change in population size. Okay, derivatives mean change. So we have the derivative of p and t here. P and t, probability that there are n cells at time t. This guy here, I can sort of explain. How many cells are there if there are one fewer than n? There is n minus 1. At what rate are they dividing? They are dividing at rate r. And then the probability that there were that many cells is p n minus 1t. And from above, it looked exactly the same. We had n plus 1 cells. They die at the rate delta. And then we have a probability, some probability that it was n plus 1 cells at that time. And the flow out is basically, we have n cells. They either, oh, this is supposed to be an r. So they can either divide or die and leave being n cells. So, yeah, this is how you read this equation. I know that this is a lot more comfortable, I hope. But let's summarize this. So the probability that a random process is in a certain state, for example, population size, that can be described by a differential equation. And have anyone here done like theoretical chemistry, like chemical physics, something along those lines? A little bit. Have you heard about the master equation? Okay. You have? Someone here? Okay. It's a thing in chemistry, and it's exactly the same thing that I derived here. I just hope that we might have a chemist in the room. Okay. So that was population size modeling. So now let's move to space. So now, instead of just counting how many cells we have, we also keep track of where they are. Because just modeling the probability of having a certain population size is rarely sufficient. We can, for example, have spatially heterogeneous tumors. A spatial model of a tumor can take a lot of things into account, but every spatial model of a tumor will have three, what I will call, load-bearing pillars of cancer modeling in them. And you will be sick to death of these three words here. Wait, I've only shown one of them so far. So the first one is diffusivity. And diffusivity is a measurement of how quickly the tumor will infiltrate its surrounding. The second one is the growth rate, and that represents proliferation rate. So it's basically how fast does the cells divide. And the last one is the carrying capacity, which is a bit more abstract, but it represents the maximum density of the tumor. It will make sense in a bit, I promise you. And these three guys, diffusivity, growth rate, and carrying capacity, if you remember when I talked about mathematical models earlier, they make for good parameters. They're clearly defined what role they play in the model, and they are usually measurable by observing the real world around us. So, why would we want a spatial model of a tumor? It allows us to forecast future behavior of the tumor. Like, for example, metastasis and infiltration risk. And the spatial model can also make it possible to learn things about a tumor. So, for example, you can take a slice of a patient, you can measure some parameters on it, mathematically in the lab, and then you can, for example, find links between, this tumor is very diffusive, and see if that is linked with some type of special gene expression for that patient in particular. And some clinicians, like one or two, use methods where a mathematical model is used to simulate outcome in different radiation dosing strategies. And here's an example of a very, very good review article, actually. It's called The Mathematics of Cancer, Integrating Quantitative Models. And it basically reviews all methods that are available for how you can have a model of the tumor and a model of the treatment and then plan treatment accordingly. So the question, why does cancer behave the way it does, is at the burning core of cancer research. And I come from a very different background than bioinformaticians in how I want to answer this question. Because bioinformaticians, I assume, want to look at a bottom-up approach in this. So they look at the genetic markers, stuff like that. I'm not a bioinformatician, so I will misuse all these words. But that's how I think that bioinformaticians want to interpret why does the cancer behave the way it does. I like space models, spatial models. So I take a top-down approach. I look at the tumor, or how cells from the tumor behave in a lab anyway, and then I define them through some low-resolution characteristics, such as its diffusivity, how much the cells run around, the growth rate, at what rate the cells divide, and the carrying capacity. How many cells can we cram into a Petri dish before it says, no more, we can't get any more than this? So I'll run this again, okay? I want to burn into your mind what these words mean. I did this over the lunch, okay? Okay, so how do we formulate the spatial model? We formulate like the simplest, absolutely simplest possible model that still accounts for diffusivity, growth rate, and carrying capacity. So what we do is that we have a lattice. So a lattice is basically points that you can either be in or not be in. And we enumerate them by the letters I and J. So I enumerates along the x-axis, and J enumerate along the y-axis. And so let's say we are in this dark green lattice point here. Our nearest neighbors are the slightly less dark green guys here. So we only count these 4 guys as our neighbors, and then the other ones are like not reachable from this lattice point. Yeah, and the distance between the lattice points are delta x. That might be important later. And let's state the rules for this model. So each lattice point can be occupied by one cell at a time. And the mechanisms for then how this model develops is very similar to the population model that I showed earlier, where we had like these holding times. We were holding in a state until some random number, like random time, was reached, and then we act according to whatever action was chosen. And the difference here is that we have an extra action compared to just cell death and cell division. We have cell jump as an action as well. Yeah, holding time. Remember the word holding time. And the holding times are defined by a rate. Remember the word rate. And the higher the rate, the shorter the holding time in general. The holding time is random, but it's determined by the rate. Okay, this is the most ambitious slide I've made in my entire life. So we will go through it. So, cells will try to move to a random neighboring lattice point at rate lambda. So the blue cell, that's me right now, and this black cell here, that's just some neighbor. So we hang around, we wait for a time lambda, and then we move here. And the probability that we move to each one of our 4 neighbors is equal, so with a 25% chance, we would have tried to go here, but it was already occupied, so we just bounce back and end up where we are, end up back where we began. Okay, let's remove the blue cell and bring out the yellow, should be brown cell. So cells will also try to divide and place their daughter cell at a random neighboring lattice point at a rate r. So move with rate lambda, divide with rate r. So it hangs around, we trigger a birth, and now we have a baby over there. But it will also try to place its baby at either of its 4 neighbors, and if it tries to place it where the neighbor, well, where we had a neighbor at a lattice point that was occupied, the cell division fails. So no birth took place. And cells will also try to die and disappear from the system at a rate delta. So R and delta mean the same thing as they did before, but now we have the lambda as well for jumping. And yeah, we waited for delta there and he died. So now that lattice point is free. Okay, and these are rules. With rules, you can create algorithms. So I will now show a little simple algorithm for how we can simulate a population with these rules. So let's say that at this time, there are capital N cells in our system. And we enumerate them 1, 2, 3, 4, 5, 6, all the way up to capital N. And we call individuals little n. So now it's time t. We look a little time delta t into the future. And then we will begin with calculating the probability that something happens in this time interval. So the probability is given by that, but you don't need to care about it. That's just what the probability is, if you want to implement it yourself. So we calculate this alpha 1, and then we generate a random number g1 between 0 and 1. And then we ask ourselves the question, is alpha 1 greater than G1? If it's not, then nothing happened. If it is, then something happened, and now we're going to determine what happened. So what happens then is that we pick one of our capital N cells randomly, and then we generate a second random number G2, and that one is also between 0 and 1. And this random number will determine what happens to this cell. So it looks kind of like this. I know this arrow isn't straight, but come on. G2 is between 0 and 1. So we have these proportions here for like how probable is moving, how probable is dividing, and how probable is dying. So we take our G2, and it ended up in the division. In the division span of the like probability proportions. Yeah, that's what I meant, proportions. Okay, so now cell N will try to divide, and we update the time, and then we go back to the top and do this over and over and over and over and over again.
Can I ask a question?
Yes.
On the previous slide, when you have this like blue, brown, and orange.
Yes.
Besides this, is it something you think?
Yeah, so what basically this means is that moving is the most likely outcome, and then dividing is the second most likely outcome because it's bigger than the orange, and that's the death outcome.
But did you pick it just because
yeah.
This makes sense? It's not this, or is it coming from some other equation?
I picked it because it kind of makes sense. Yeah. Yeah. So yeah, every parameter for everything. I'm going to show like some simulations and stuff. I've just like pulled them from somewhere. Okay. They came to me in a dream. They're not exactly based in anything. This is just like a tutorial in how this model works. So let's simulate this. So we initiate a 100 times 100 grid as our simulation space. So we have 100 lattice points in the x direction, 100 lattice points in the y direction. And then we initiate our population in the 50 by 50 grid at the center. And we say that the probability of there being a cell in each of these grid points is 1/3. So the yellow dots here are basically cells, and the blue dots are empty lattice points. And then I ran this for like 1 million generations, and we skip like to every 1,000 because it would be very, very boring to look at a 1 million frame GIF. And yeah, so this is how it looks when we run this algorithm that I just described. It doesn't really look, like a Petri dish yet, because it's a very, 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 very simple model. But it's a start. It's something you can modify to get at something more realistic later. And remember when we balanced probabilities earlier? We were like, what's the probability of there being n cells at time t? Let's do this for this system here. But now, what we are interested in is the probability of there being a cell at lattice point ij at time t. That's a long sentence, so let's call it pijt. And yeah, this is a warning slide. It has a red background, which is the danger color in nature. Because there will be some pretty heavy mathematics on the next few slides. But our goal is basically to formulate an equation for how this thing evolves. Probability of there being a cell at lattice point ij at time t. Don't worry if you can't follow the derivation, because I will try to hammer in how to get an intuition for how it looks later on. But the strategy is basically the same as before. We take a little time step delta t, we approximate like how probable every different outcome we can have is after this little time delta t, and then we create a differential equation. A differential equation is an equation that involves derivatives. Okay, so now we look a bit into the future, and we want to say, what's the probability that this lattice point ij is occupied in this little time into the future? So a good strategy here can be to think about what can make it change. And the things that can make it change is that some cell division occurs, cell death occurs, or a cell migrates there, moves there, diffuses over there. So I color-coded division as brown. So let's create a brown box and say, okay, so like in what way, in a sentence, in what way can a cell division lead to there being a cell at this lattice point now? And the sentence is like this. The lattice point has to be free. It can't be occupied. That's the first thing. The second thing is that some neighboring lattice point, so if we are at ij here, we mean these 4 neighbors here. The second thing is that at least one of those guys has to be occupied. And after we have determined that, okay, that guy is occupied, then we have that at least one of these guys have to decide to divide in that time interval. And after that, it has to place its daughter cell at ij. So if we had a neighbor here, and this lattice point is empty, and it decides to divide in this interval, it has like a quarter chance of placing its offspring here, and a quarter chance of like putting it there, and there, and there. Okay, so that's like how you can think of like, okay, what's going on here? What's going on? Okay, this is probably the way that we can land at there being a cell here from cell division. Then we have cell death. Now we have a minus sign because cell death will remove probability of there being a cell there. So like minus removes probability. And then we have that ij is occupied, but it dies during this time interval. So migration is that ij is free at this time and some neighbor decides to jump there. So we write them down as sentences. And the last thing that can happen is that this lattice point is occupied and nothing happens in this time interval. And I am actually going to torture you a bit because we are going to zoom in on this event in particular, and we're going to calculate how probable it is. Well, I'm going to. You're going to sit there. Okay, so here we have the sentence. ij is free, some neighboring lattice point is occupied, the cell there divides, and it places its offspring in ij. Okay, so how probable is it that ij is free? Well, it is 1 minus the probability that it's occupied, because the probabilities has to add up to 1. So if it's pijt probability that it is occupied, then it's 1 minus pijt that it is free. Okay? So that's the first part of the sentence. The second part of the sentence is the probability that some neighbor, I've just used like plus minus signs here because I didn't want to write out all the neighbors, is occupied. Well, then that's just the probability that they're occupied. pi plus 1, j plus 1, t. And then we have the probability that the cell that is hanging out at that lattice point decides to divide. And that's about the rate, the division rate times the time interval. It's not exactly that, but it's close enough. And then we have the probability that it decides to place its offspring at ij. And that's a quarter, because it has 4 neighbors. And it has no preference right now. So we multiply all these probabilities together. And then we get the probability for this event. Cool, that was the brown box. Let's do that for the red box, the blue box, and the black box. And we have all these probabilities written down at the bottom of the slide here. They're so low down you can't see them if you sit in the back, and that's the point. So after we have calculated all these things, we do a whole lot of boring algebra, adding these things together and simplifying. And the boring algebra looks something like this. And then we're done. So we have now arrived at an equation for the probability that ij is occupied at time t, the change in probability, a differential equation, an equation that involves derivatives, and derivatives represent change. And that is a flow in from neighbors dividing. I know that like probability flow probably sounds a bit hippie, but that's the lingo. And then a flow out of probability from cells dying here. and a flow in and out from cells randomly running around. And yeah, then there are some miscellaneous round-off terms. Don't worry about them, okay? They will not be important soon. And it looks like this. And the slide is red, okay, so you don't have to read. It just looks like this. But I've color-coded it at least. So the green is the change, the derivative. The flow in, cell division, modeled with the brown. Flow out from cell death is orange. Moving around, that's a big one, in blue. And then these miscellaneous terms, they're just glorped up by this ordo, is it called in calculus, if you've taken a calculus class. Ordo is like a mathematical trash can. You just throw terms that you know will not be important there. Okay, still a red slide, so you're allowed to think about something else for a while. So what we will do is that we will shrink the lattice. You might remember that I said that the lattice points are spaced with a delta x between them. So we let delta x go to 0. That's what this delta x arrow 0 means. And then we make a little change here. So lambda, the jump rate, will now be replaced by something that depends on the grid size and this new coefficient d. This is called the diffusion coefficient, d as in diffusion. And it's a measure of how much you randomly move around. If you remember the blue box that says diffusion, and then, yeah, it was diffusing. So now we forget about lambda. D is our new best friend. Yes. And then we also shrink delta t, just like we did with the population size model. And yeah, when we do this, and there's some under the hood stuff going on, we have arrived at the most fundamental equation in all of spatial population dynamics. It's like the holy grail of spatial models for how populations move through an environment. And it's called the Fisher equation, and it looks like this. So you recognize this perhaps as a derivative. I said it on here's the derivative slide. It's just a different way of writing it. This upside down triangle is kind of a derivative. Don't worry about it. And pxit, xyt, is the probability. No, it's not probabilities anymore because there's been a change, whatever. It is the, okay. I will explain the terms later. I will first give some background of this equation. So yeah, it's called the Fisher equation. It's an example of a partial differential equation, and it's fine if you've never heard that word before. They usually show up maybe in your second or third year of pure math studies in university. And this guy was first formulated in 1937. It was used in ecology first, but it's been like widespread. Like all parts of mathematical biology have the Fisher equation as its like cornerstone almost. It's a super important equation. Of course, it's derived from a model that is grossly simplified, but it is very modifiable. And if you understand what the different terms in this equation mean, you don't actually need to be able to solve it. You will just be able to read. Like the D here, that's diffusion, that's random movement. How much is this population milling about? The R here, that's the growth rate. That's like how fast do they reproduce. The delta, yeah, that's how fast they die. And K, which I kind of just snuck in here because I didn't want to show where it comes from, but that's the carrying capacity. So yeah, I felt it was time to like remind everyone of like what the rules of the game are. We have migration in blue. We have division in brown. Division can fail. I think that animation is funny. And we also have death. And this slide dies now, yes. Okay, so let's go through like what these parameters should be interpreted as. And after that, because I don't like to listen for 90 minutes straight ever, we will take a break for like 10 minutes and then we will be back. Because I will probably not be able, I've removed a third of the slides from this slideshow, so I will not be able to fill all 90 minutes either way. Yeah, so the parameters in this equation, okay. P, X, Y, T is the cell density at the point xy in space at the time t. So we have space, it's a two-dimensional space, so we have an x-axis, a y-axis, and this gives like the cell density at a point in time, at a point and a time. D, the diffusion coefficient, measure of how much random movement the cells are up to. Delta, death coefficient, corresponding directly to average rate of cell death. And R is the growth rate coefficient corresponding directly to average rate of cell division. And K is the carrying capacity, which is a measurement of the maximum population density. So you don't need to care about all the scary signs. You only need to care about the D, the R, the K, and the delta. That's like, they represent something very specific in the population. Yeah, I even made a table here, change in cell density, this. Contribution from diffusion. How much does it contribute to change? This much. Contribution from cell division. How much does that contribute to change? This much. Contribution from cell death. How much does that contribute to change? This much. Because right now, okay, we'll take the break here. 10 minutes, yeah. Very, very, very basic. But we're going to modify it a bit soon, and make it less basic. Okay, so the Fisher equation, so like a solution to the Fisher equation should be interpreted as the average behavior of the corresponding lattice-based model that we derived it from. So here's the simulation that I showed you earlier, and that's just one realization of this. So here, we are looking at the average of 50 runs of that simulation. So this is like let's call it like a sample average type of thing. We just run the simulation 50 times, and then the heat map goes from like blue through green to yellow, and that's like how much cells are here, like at average over these 50 simulations. And the Fisher equation is like the theoretical limit of if we have an infinite number of simulations of this particle system, a solution to the Fisher equation gives that average. So we can see here that in this panel, we have the average of 50 solutions, and in this panel, we have a solution to the Fisher equation with the same coefficients, parameters, and initial condition. So the initial condition here is that the 50 by 50 box in the middle, or it's 0.5 by 0.5 in this case, is at 1/3, because that was like the probability of there being a cell in each of these lattice points. And then it kind of develops in the same way that the average of 50 simulations develop. So that's the interpretation. It's the average behavior of a population that we have set some rules for how their dynamics work. Yeah, that was the next slide. Okay, now we're going to extend the Fisher equation, put your local mathematician to work, but also this is kind of what the practical part of this workshop will be about. So we will do some modifications to this equation system. So let's say that we have a heterogeneous tumor. It has multiple phenotypes. And so let's say it has 2 different phenotypes. We have phenotype 1, and that's like a base level phenotype in this example. It has like the same diffusivity, division rate, and death rate as what we just saw. And then phenotype 2 has like drastically reduced diffusivity and division rate, but also a much lower death rate. So they have like some different behaviors. We can think of phenotype 2 as a more resilient mutation of phenotype 1, maybe. So a simulation of this can look like that. And here in yellow, we have like the first phenotype. And in blue, we have light blue, we have the second phenotype. So this is a way that you can like model heterogeneous media, basically, that you basically just add another population and tweak its parameters a little bit I've done this in MATLAB because I'm a dirty MATLAB scrub, but there are great like software that are like purpose made for cell simulations. There's like one called Physicell that I was thinking about introducing, but then I realized it has a learning curve of like 400 hours, so I didn't. Yeah, but writing down like the probabilities of everything happening is a bit of a nightmare for when we start adding a lot of different populations. But writing down the differential equations, like the Fisher equation for it, is quite easy. And the easy comes with an asterisk and terms and conditions apply. I know it's probably not that easy, but it's easier. Okay, so let's look at the partial differential equations where we have more than one cell population.
Can I have a quick question on the previous slide, actually?
Yep.
Since we are like modeling based on like a specific space, not like we are not like agent-based following cell, just modeling space. So how do you add clones in such a model? So like
Clones? Or?
like populations, yeah, different populations.
Like in the simulation that I just showed, I just added like, yeah, so basically like the first population I store as like a 100 by 100 matrix, which is basically like it's a 1 if there's a cell there and it's a 0 otherwise. I just added like another matrix and then I made them talk with one another so that they don't overlap.
Okay, so like basically modeling like, okay, so they're like independent, not like they're competing?
They are competing because like the phenotype 1 cells still like have to check if there's a phenotype 2 cell occupying a lattice point if it tries to jump there.
Okay,
yeah.
So that's the competition part. Okay,
yeah.
Thanks.
And you can of course model competition more in a more involved manner. You can do all kinds of things with the Fisher equation, which we will now see. So we have these two phenotypes. We denote them. I actually accidentally changed the color compared to the last slide, but I'm too lazy to change it. So we denote phenotype 1 with a P and phenotype 2 with a Q. So for P, the first phenotype, it's the exact same equation as before, but I've added like a little 1 subscript to the important parameters here, except for the carrying capacity, because that's more of like an environmental thing than a cell thing. And it's like, this is the diffusion coefficient for population 1. And then we can do we add another row for the Q population. Now we have 2 partial differential equations here. And these are usually nightmares, but these guys are kind of easy to solve. And also what we can note here is that in the carrying capacity here, we see that it says P plus Q instead of just P as before, because they are both contributing to filling out all space. And as an example, like if you look at the parameters here, phenotype 2 is slower than phenotype 1 if the diffusion coefficient for phenotype 2, D2, is less than D1, the diffusion coefficient for phenotype 1. So you can like model like a heterogeneous population where one is slower than the other one by just tweaking the diffusion coefficients up and down compared to one another. And it's super tiring to write this X, Y, T all the time. It will always be there. So I will do a sick math trick and we will just ignore them from now on. So instead of writing P, X, Y, T, we just write P. It's a shorthand. Makes it look even scarier, right? Oh my God, we're just starting. So this was a way that we can model like 2 phenotypes competing for space, but they're not really interacting with one another in any other way. So let's add some interaction. Notice that in the color coding here, I've added yet another parameter called switching. Yeah, we can keep adding stuff to this system of equations. So let's say that phenotype 2 is actually like a mutation of phenotype 1, and phenotype 1 cells, they switch to become phenotype 2 cells at a rate that we call sigma, and it's purple, if you can see. So this equation will then look like this. So it's the normal Fisher equation. So we have the diffusion with the funny upside-down triangle guy. We have the growth rate, we have the carrying capacity, and I could not get the division line to not be green here, so just bear with me. PowerPoint. We have the death rate, And then we have a minus sigma here. So what this basically means is that at a rate sigma, the P population leaves being P, and it gets added to the Q population. So that's why there's a plus here and a minus there. So that's like a way to model mutation. You can also like model maturation in this way, that you basically just, okay, so if I mature from being like in this stage to that stage at a rate this and that, you just add like a minus from the one you are leaving and a plus to the one that you are arriving at. Yeah, so the intuition here, phenotype 1 leaves, hence there's a minus sign, and turns into phenotype 2, which adds to the population density of phenotype 2, so there's a plus here. And let's add even more. Yes?
So what's the difference between switching and migration? Because to me it would seem like migration, like if you lose something, it goes to another, so it would seem like sigma, for example.
Okay. I mean, the migration is basically just that they are running around. The important thing with the switching is that P and Q is like the population density of two different population types. So we have like two distinct phenotypes. It can, like one model that I haven't included here, I removed that slide, is like go or grow, which is that in some cell populations, like when a cell is ready to divide, it slows down, and then it will like sit there and grow, and then it divides. So a way to model that would be like that the grow population has a much lower diffusion coefficient because it doesn't move, and you leave at the rate sigma and become the slow dividing type. So it's like, this is like a flow, because there's a minus sigma p here, from the first population to the second population.
But isn't that like the term migration basically, or it's different? Because migrating is moving from one place to another, right?
Yeah, but this is not moving in place. This is moving in type. It's like you move from being a phenotype 1 cell to being a phenotype 2 cell. So it's like a different type of moving. But we basically just slap a little minus sign here and a little plus sign there, and that's the simplest way of modeling it. Okay, let's take something that is near and dear to my heart, which is modeling cooperation. So now purple is cooperation instead of switching, which it was before. And now we only have one population. We don't have a Q population, we have a P population. So the cooperation kind of works like this. The cells in the population, they emit a common good growth factor, and some of you guys might know what these guys are actually called, like the chemical compounds. I've read it, but I've forgotten it because it's chemistry, so it's very complicated to remember long names. So basically, what this growth factor does is that it provides a boost to the division rate of your neighbors. So I've blocked out like the division rate part of the Fisher equation here. And then I'm going to say that, okay, so how do we model this? So one way could be to do this. So we have the base division rate, R1, that's the same as before. And then we get a boost from having high population density, which is R2, and R2 is then multiplied with the population density, because if the population density is low at some point in time, then this will not like contribute a lot, but if the population density is high, then they will emit a lot of growth factor. And I choose like a linear function here, which is basically just, plus R1 plus R2 times P. That's a linear function. You can draw it as a straight line. But you can use any increasing function here to model cell growth or cooperation in cell populations. And as a matter of fact, a hit paper very recently published in the Journal of Theoretical Biology, so recently that I have to screenshot the preprint here because it was yesterday. Actually proves mathematically that this is a way too simple model to account for even basic like in vitro situations of cancer cells milling around. Yeah, it's me. Yeah, but I have super fun like modeling like cell cooperation stuff. You can also, if you like game theory, you can like introduce some strategies and games and stuff into this thing. We are not going into game theory stuff now. We're keeping it as simple as possible. Okay, so exhibit 4, the last exhibit. We will now go back to the case where we had 2 types. Oh, there's no cooperation anymore, so this one is wrong. This one shouldn't be here. This should have a different name. So yeah, we have 2 phenotypes. We named them P and Q. And there's something special with Q this time, okay? It's extra nefarious, because we want to treat this tumor with radiotherapy, but the part of the cancer cell population that is in phenotype 2 is completely immune to it. It's like it doesn't care. You can irradiate it all you want, it won't kill it. So we do it anyway, so we bombard the tumor at some time, capital T, it's like just some time, maybe 24 hours from now, and that will lead to an increase in death rate for the P population, so the susceptible, oh my god, the weak phenotype. And like when I think of like, okay, let's just formulate a reasonable model, I literally dreamt this up. It should probably look something like this. So we have like a base death rate, and then when we apply the dose, it should spike, because these guys in the first phenotype, they will start getting murdered at a very high rate by the radioactive burn, radiating anymore. And yeah, here's the equation for that. I'm not going to explain it, but this function that I wrote here basically does exactly what I said, that it gives like a short burst, and then it fairly quickly returns to normal. So yeah, so the model we have here, it accounts for a big risk in radiotherapy. And yeah, now we get to the evolution part. Because you can put evolutionary pressure on the tumor to like focus on the resistant phenotype. So like if our dose is too aggressive, something like this can happen. Susanna, where did I steal this picture from?
No idea. I mean,
It's yeah.
It's just in every paper on adaptive therapy.
Yeah, it's used in every paper in radiotherapy.
No, on adaptive therapy.
In adaptive therapy, yeah. So here's the situation. We have a tumor, and the blue cells now are weak, and the pink cell is resistant. And then we blast it. So now there are more resistant cells than weak cells. And that means that in this situation, where we blasted it with the maximum dose, the tumor becomes resistant, and we can't treat it with radiotherapy anymore. So in an adaptive therapy setting, you blast it with like a smaller dose, so that you make the tumor smaller, but you don't kill off so many of the weaker phenotype that the stronger phenotype completely takes over. And then you can keep, basically by jutting out bursts, you can keep the tumor size under control and not let the resistant phenotype completely take over. So you don't end up in a situation like this. So now I think the weak phenotype is in blue because I changed the colors. But the situation here is that there, I bursted. And we went from having much more blue than yellow, yellow is resistant, to having much more yellow than blue. And that's a bad situation, because we killed too many of these guys, the blue guys, at once, which made them like unable to compete for space with the resistant phenotype. And I think you will do an exercise on this later. Is that true, Jada? Is it still true?
Yeah.
Okay, sure.
A simple version of this.
Yeah, it probably doesn't look exactly the same. As I said, it came to me in a dream. I just wrote it down. So that's like a thing with mathematical modeling. Like after a while, you start thinking in functions. So like if you hear a behavior, you're just like, okay, you write something down and it will probably match that. And I hope like the goal of this session is to make expressions perhaps not as complicated as this one, but a bit easier, like readable for you. So you understand what like the parameters, what they represent. Yeah, wrapping up. What was all this for? Has anyone seen it yet? So the cat has increased in intensity with 2% per slide or per per section slide. I thought you would see it earlier. Okay, so what have we done? We're wrapping up. In this workshop, I have given an example of a simple simulation model of a cell population. So yeah, the cells can like move and stuff like that. And yeah, they can also collide with one another. That's important. Bonk. We have also seen how such a model connects to a partial differential equation called the Fisher equation. And if you remember, here is like the average of all these simulations. Here's the solution to the Fisher equation. And the Fisher equation describes like average population dynamics. And what this equation does is that it takes 3 key low-resolution parameters of tumor progression into account, and also the death rate, but that's not as exciting as the other ones. The diffusion, how much the tumor moves around in space, the growth rate, which is how fast the tumor, the cells in the tumor divide, and the carrying capacity that encodes the maximum density of the tumor, usually because of competition for space and nutrients. And then we finished with demonstrating how one can modify the terms in the Fisher equation to arrive at perhaps more realistic models that are also like more useful in a modeling setting. And real tissue, of course, is incredibly complicated, and it requires a variety of modeling strategies to simulate convincingly. So even like these equations with like 2 species that are competing and maybe they're like doing some other fun stuff, they are more theoretical constructs, and if you want to have like accurate models, like in a digital twin setting type of thing, yeah, they become huge, these type of models. But the core idea behind how you formulate the equation remains the same. You have random movement, growth, maximum capacity, and death. And like these are the phenomenological things that define a tumor when at least me and my stupid mathematician brain sit and look down a microscope, or pictures taken with a microscope. Okay, thanks for your attention. Now enjoy your break that you already had, but enjoy another break, I guess.